Well, I'd like you to join me in giving a special welcome to Dr. Walter Veit as he joins us now and makes his presentation.
Good evening, everyone. We're going to talk about origins tonight, and it's a sensitive issue, and some of you might even battle with what Americans call my accent. Of course, I think it's the other way around. I think you have the accent, and I speak the English, but nevertheless. We're going to talk about origins in 4 parts. In this first section, we're going to talk about rocks. We're going to talk about the age of things. In the second section, which follows just after a short break, we'll be looking at some of the fossils. Now, some people are not as keen on rocks as they are on fossils, but nevertheless, if you stick around for the second session, then we'll have dinosaurs in there and all kinds of interesting fossils. Tomorrow, we're going to speak on the evolution of man. We're going to talk about the ice ages. We're going to talk about the woolly mammoths. We're going to talk about all of those things. And then we're going to look at origins. We're going to look at the whole picture of simple questions. Is it possible to believe in our age of an ark? How did all the animals get into the ark? I mean, that's so improbable. Where do all the races of men come from? How do we have this great genetic variability? Those questions we will answer on the next day. And the third session will also deal with aspects of the creation account, some very, very interesting questions we'll try and answer as to why we're here in the first place. I mean, did we ask to be here? Are we an afterthought? Are we part of a program? What's the situation? We'll look at some of that. So I invite you to sit back and fasten your seat belts and enjoy yourself. The God factor, science. Today there is a major conflict between the two. On the one hand, you have creationists who believe in a short chronology and creation, ex nihilo, God spoke and it stood fast. And on the other hand, you have the idea of millions and millions and millions of years of evolutionary processes bringing about the evolution of everything that we have on this planet. And the two ideas are very, very remote from each other. There's a group of people that try and marry the two, that sort of get in between the two. We call them theistic evolutionists. In other words, the Genesis account is basically time periods, long time periods, and God started the process and kept the ball rolling more or less in the right direction. And then through evolutionary processes, we have the origin of everything that there is, including man. There are a few basic problems with that. Number one is the time sequence is way out of sync. For example, the plants are there then millions and millions of years before there is a sun. And you could have a problem with that because of day 4. Another problem that you could have with that is that evolution requires the survival of the fittest to the detriment of the not so fit, which then leads to extinction. And the biblical account says that death came in as a consequence of an action of man, which is defined as sin. So you run into all kinds of problems to reach the compromise. Nevertheless, we have all those groups in the scientific world at large. I would say the largest body of evolutionary scientists do not incorporate God into their model. And I myself was an atheist and an evolutionist for many, many years. I taught evolution at the graduate level for 19 years. So I'm very acquainted with the idea, and I was very convinced of the idea. And so we're going to contrast the two. Now, sometimes people will say to me, now hang on a second, I would like to see both models receiving equal exposure. And that is unfortunately not possible in the time frame that we have. And in any case, let me point out that the one model, the evolutionary model, gets more than its fair share of exposure. You switch on a television set, you go to any museum, you go to any school, fraternity, what have it, university, and the very first words you will hear will be of an evolutionary nature. So everybody is aware of it. They see it in movies from morning till night. So grant me a little bit more exposure to the other view this evening, although I will try and do justice to the previous view as well. Otherwise, I would have to say that I was off the wall when I was an evolutionist. And obviously, I thought I was pretty normal, or so I thought. All right, the God factor. Do they really get along? I found this little letter in one of the letters to Time magazine quite interesting. Moses was hated in his day because he told the truth. If he lived in these dark times, he'd be twice as hated. And I wondered, why did Time magazine put that one there? If you take man as an entity and you look at the complexity of this creature, then it really is quite incredible, if you think about it, that such an organism, which is so complicated that it took a body of scientists worldwide to try and just figure out the basic physiology over the last millennia. And what we know today is really a fraction of what happens in that organism. And some of the mechanisms that operate in this organism are so complex that if you work out and compute the probability of these things coming into existence by processes governed by chance and then natural selection, well, then it really does boggle the mind, and we will see in the fourth lecture that there are some major problems. Mankind today regards himself at the pinnacle of the evolutionary process, having evolved intelligence, the capacity to put people on the moon. But of course, everything, according to the theory, has its origins right down there in a primeval soup. And if we go back even further, we can go to a time period in the history of the world when at some stage science says there was a Big Bang. And this Big Bang consisted of all the matter that is now present in the entire universe, compacted in a dot smaller than the size of an atom. Well, it varies. Some scientists say the size of an egg. And from there, through the eons of time, all matter had to arise. And from then on, all organic evolution had to take place until we have organismic evolution, animals and plants and creatures coming into existence. And that is basically in the last fraction of time. Now, evolutionary scientists have a model for the evolutionary process. And let me put it to you quite frankly. It is a logical model. Do you think that all those bright scientists out there would follow something that is not logical? But logic is not always right. There is a vast difference between logic and what is right. Let me give you an example. If I give you a bag of dog skulls, and you had never seen dogs in your life before, never seen them before, and you are taking this bag of dog skulls back to your museum, wherever it is, Venus, Mars, who cares, and off you go, and you are now going to arrange them in the sequence in which they evolved. How would you arrange them? Every dog skull that exists, how would you arrange them? Well, you would sit down and you'd compare skulls, and you'd probably end up with a picture arranging them from small to large. Is that right? You'd put them on the screen and you'd shape them and compare them, and bone features and anatomical features, and eventually you would have them from small to large. Anyway, there's a law in science which is called the law of Carroll, which says everything evolved from small to large, which is very logical because you don't start evolution with an elephant and end with an amoeba, right? You go from an amoeba and you start going larger and larger. So you would arrange it from small to large and put it up in your museum, and everybody would say, wow, that's great, that's logical, but would it be right? Well, nope, would be absolutely wrong. Because we know that the dogs of this world have in recent times been bred from wild-type creatures like the wolf. And that what you have is variety in the gene pool from small to large. So what is perfectly logical does not necessarily have to be perfectly right. So let's talk about this geological column. The geological column is the layering of the rocks that you have in the world out there. If you go to a road cut, you can see some of the geological column. If you go to a canyon, you can see more of it. And down here on the left, from the Cambrian, which are the rocks at the bottom, which contain the macrofossils, all the way up, all the way through these various layers until you get up here to the Triassic and the Jurassic. And you all know about the Jurassic because of the movie Jurassic Park, right? So if you have a look to the right, then you will see, wow, the dinosaurs roamed in that time period. And as you go up higher, you come to the tertiary layers, the Cenozoic, and in the top layers, you have the birds and the mammals and man. So you have the sequence of fossils in the rocks as well. So two problems. Number one, you have a sequence of rocks, layers of rocks. Where did they come from? And you have a sequence of fossils in the rocks. Where did they come from? Science says the rocks are a record of time in the history of all geology. So that's a record of time. So when the Cambrian was present, that was the surface of the earth. Then later, through periods of sedimentology, you got the next layer and the next layer and the next layer. And in the Triassic, that was the surface of the earth. The top layers had not yet been formed. And then the next layer and the next layer and the next layer. So that is what is determined by science. And of course, each one of those layers also contains fossils. So science says the order and the sequence of the fossils represents the evolution over time. That clear to everyone? That's basically the basis for the entire evolutionary theory. And because mutations are normally harmful and mutations have to take place by chance and the probability of getting good ones is pretty remote, there's a lot of time involved in this whole sequence. So generally speaking, we count anything from 600 million years since the Cambrian to the present for all of this to have happened. That's the theory. Now in the first lecture tonight, we're going to look at this side of the column. And we're not going to look at the fossils at all. But hang around for the second presentation, then we'll talk about some of these fossils. So first the rocks. Evolutionary theory is a theory which sort of takes creationism with a pinch of salt, even ridicule. So you'll find things like this in the science magazines of the world. Creation theory, and of course, the idea in this New Scientist presentation over here is that we actually did evolve from ape-like creatures, and that eventually, once we don the glasses and look intelligent, then we look for a higher origin, just to give us some some bravado. Or this one also comes from a science magazine, New Scientist. Sorry, but we've just realized that you're an irrational projection of our collective unconscious. So God is marginalized. And then the tables are turned. In this one over here, it says, is science in your life? You know, like a minister would go and say, is the Lord in your life? So scientists come to the minister and say, is science in your life? So basically, there is a sort of measure of truth in it, that there is more than meets the eye in this theory. Let's briefly run into the past. Let's speak about origins. If you look out there and you see all the myriads of stars and all the galaxies, you ask yourself, where did they come from? How did it all start? Science comes up with the Big Bang model. According to this model, at some stage, as I said, right here in the beginning, there was an explosion in this totally compressed area, a black hole with the entire substance of the universe compressed into this pinhead. And this exploded in this huge vacuum, which we call space. There was no matter, there was nothing. There was just a huge burst of energy and a massive explosion, tremendous heat. And then as it expanded, it cooled, and eventually the first particles started forming. First the subparticles, then the first particles, then you started getting the protons, and once you had a proton, you had hydrogen. And then these hydrogen gas clouds in this vacuum would coalesce upon each other and eventually, through gravity, coalesce and again form a star. And in that star, you would have nuclear fusion. So all the atoms and elements that we have in the world today had to be formed then in a star. That had to again explode in a supernova. Boom! Putting all this new matter in the form of dust into the atmosphere, into the space. Out of that had to coalesce new stars and planets. And then eventually you could have the matter that it takes to make life on this earth. Well, the Big Bang Theory is not as simple as people would have us believe. And there are major problems with it. We haven't got time to deal with it. I just want to show you an article in the journal Nature, that's the top science journal in the world, which says the Big Bang, not yet dead, but in the decline. It goes on to say there is a crisis in cosmology, and that there are ages of the universe which imply that stars are actually older than the universe should be. So there are major problems with this theory. Well, I'll give you one example. If I have an explosion in a vacuum, do you think it's possible to take the gas that spreads out in a vacuum and make it come together again and form a star? If you pop a balloon, can you gather the gas together again and compress it into a point, yes or no? Have you tried that? Well, you take a bicycle pump and go, what happens? Do you compress it? Can you compress it, or does it push out? It gets to a point where you can't push it any further, right? So the pressure outward is always greater than the attraction inward. And so there's a major problem to get it to coalesce. Secondly, if you have an explosion in a vacuum and it goes out linearly, pow! Why is everything in the universe in clusters, superclusters? Why is everything going round and round and round instead of just shooting out from the center linearly into everything? Millions of problems with this theory. Okay, so let us say, for example, give them the credit, let's say it happened, for argument's sake. And here we are. Now, what we have to show our origins is what we can see in the world out there today. If I go and I touch a rock, if I pick up this rock, I can say, well, how did this rock come into existence? What are the circumstances that led to the rising of this rock? How did the fossils come into existence? Those are questions I can actually go hands-on and study in the environment. Now, the Bible says that this world was destroyed by a worldwide flood. Is that correct? Okay, that's what the Bible says. Science says there was no worldwide flood. Life was never destroyed on this planet in totality. They will admit maybe to a local flood. I have a problem with that. What's the point of building an ark and putting all the animals in the ark if there was just a local flood and the animals were surviving out there anyway? Does that make any sense? Not to me. So there are big differences in these two approaches. Science says that the layers in the geological column point to millions and millions and millions of years of evolutionary process. And that when the bottom layers were the surface of the earth, it was much like it was today. And the next layer, much like it was today. And the next layer, much like it was today. So what we have today is a record of what we had in the past. Whereas the Bible says everything was destroyed and must have evidence of a worldwide deluge. Doesn't that make sense? So what can I prove? Can I go back to the creation itself? No. I can only look at what there is now. And if I look at that, then I can only look at what the rocks have to reveal. So let's just run through the biblical chronology of the flood. If you ask anybody, how long was the flood? What's the normal answer you get? 40 days, 40 nights. That's not what the Bible says at all. The Bible says that Noah entered the ark, and for the first 7 days, nothing happened. And then for 40 days and 40 nights, it poured. There was a deluge. 40 days and 40 nights. But the waters rose upon the earth for 150 days. That's about 5 months. That's almost half a year that the flood waters rose. Question, where did that water come from? Well, we go back to the Bible. What's the Bible say? Where's it come from? It rained 40 days and 40 nights. That's not enough because it rose 150 days. But it says that the waters of the great deep burst forth. So there must have been explosive tearing up of the earth's crust. The water shot out from the fountains of the deep. And the book of Amos says, who is like unto the Lord, who takes the water of the Tehom, and referred to there as the ocean, and pours it over the land. So is it possible that you actually had depression of the continent, upwarping of the ocean floor. So you had this sort of activity. You had pouring of the materials in the ocean onto the land, breaking up the continents at the same time and flooding it from the top. That's major geological upheaval. Then the Bible says, after that, the waters started to decline, and then you can take the age of Noah, and eventually after 1 year and 17 days, he left the ark. 1 year and 17 days. All right, let's go to the rocks. If you go to the rocks, you will find that the rocks are layered in different layers. Layer at the bottom, a layer above, a layer above, and a layer above, and a layer above. Geologists say each one of those layers is millions of years older than the next, and the next. It's called the law of superposition. So if we look at these layers of rocks, then this was once the surface, then that, then that, then that, then that, then that, etc., all the way up. And each one represents time. So during the Cambrian, you had these creatures. During the Ordovician, you had these creatures evolving. During the Silurian, you had those funny creatures. And as you go up to the higher levels, you get all the plants and the animals on the land starting to develop. Then up here in the Jurassic, you had the dinosaur and the reptiles. And in the upper layers, you have the mammals. Let us go and have a look at a section of those rocks. Now, the best one, unfortunately, always in the world is right here in the States. And the Grand Canyon gives you a great picture of the lower rocks, the Paleozoic. And I want you to look at them carefully. Can you see that you can see the layers very nicely? So here's a layer, and then there's another layer, and there's another layer. And there you can see also part of this layer that stretches across the back there. One thing that is very obvious is that the contact line between them all is very straight. Can you see that? They're like boards, one on top of the other. Gloop, 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 gloop. But remember, what does science teach? Each one of those layers was once the surface of the earth. What does the surface of the earth look like in the world today? Is the whole world uniformly flat, or do we have canyons, valleys, mountains, hills? What does it look like? Well, sure, it's not uniformly flat. So we go down the Grand Canyon. Scientists have been so good as to put up boards to tell us what happened. And here's a problem. In some places, they actually have a problem. And here's one of them. It's called an unconformity. And the problem is that you have certain rock layers in some areas which are absent in other layers. And here in the Grand Canyon series, there are some of these missing rock layers. Now, that shouldn't be a problem, but it is a problem. I'll tell you why. Because science says each one of those rock layers represents time. Is that right? So if it represents time and the layer is not there, what does that do to time? It takes it away. So obviously, if you have this notion that the layer represents time, then you have to explain it this way. You say, well, here they have a little diagram explaining what happened. The missing layers actually were there. So the layers underneath formed, then the missing layers formed. And then there was a period of erosion. So they were rubbed out in this area. Rubbed out until they were gone, and then the next layer came on top. And that's why you have a gap. And they explain that by saying there was a time of erosion. Now if you go to the Grand Canyon, and you go between this layer over here and this one's called Muav, this one's called Redwall, and you go along that line over there, can you see how nice and flat it is down there? There you go. There are 100 million years missing. Gone. 100 million years. And between this layer and the next one above, 30 million years missing. Apparently through erosion. Absolutely flat. Now, let me put that in perspective for you. The average rate of erosion on this planet varies from about 6 centimeters. Now, what is that in American? 6 centimeters. It's about so much. So what's that? About 3 inches, let's say. 2.5 to 3 inches. Of the Earth's surface to this. Just over 6 feet. So in the Himalayas, where it rains a lot, about 6 feet of the surface of the soil in the mountains gets washed down, ends up in the ocean. Every year, 75 billion tons of sediment ends up in the ocean. Let's take the lowest figure. Let's take the 3 inches. Take the lowest figure. And you take the average height of the continents. How long, at that rate, before the whole continent is gone in the ocean? Well, it works out at 10.2 million years. 10.2 million years. And we're supposed to believe that everything has been around for hundreds of millions of years. 150 million years since the breakup of the continents. Even much more, twice, 3 times that much before the breakup of the continents. And yet everything is still there, from the oldest to the youngest. It's a bit problematic. All right, so 30 million years should put it into perspective. That's enough to wash the continents into the ocean 3 times over. Here's another one. At Dead Horse Point, over here, there are 12 million years missing, absolute flat contact. Now, science says there was a period of erosion there. Above that, on that other line over there, 30 million years missing. Here's another one, a sandstone and Moen Kopi over here, these layers, 20 million years missing. Now, as I pointed out before, they're missing, they say, because of erosion. But erosion does that. Now, I found this in the Cedarburg in Africa. You can find it anywhere in the world. But this is phenomenal stuff. Very exciting. I want you to be excited. 3 layers of rock. 1, 2, 3. The bottom one, of course, millions of years older than the one above it. And the next one, millions of years difference than the one previous. So that's the oldest at the bottom, slightly younger in the middle, and the very top one over there is the youngest layer on top. Now the top one is subject to present day erosion. Can you see how nice and flat it is on top? I'm sorry, it's not so flat, right? It's quite bumpy. Why is it so bumpy? Because of erosion. If I had to put another layer, let's say I depress the continent and I have an erosion period above that, what would the contact look like? Flat or like this? It should look bumpy, is that right? But it isn't. Now what about the one beneath? What's that like? Flat. Do you think it was ever the surface of the earth long enough to have developed erosional features? Yes or no? I think it's a problem. I think there's a problem. Maybe there's another model to explain things like this. Well, let's have a look. So we say the layers are flat, like we have them over there. If we had erosion, they should look like that, right or wrong? If I put a layer on top, it should look like that, right or wrong? But it doesn't. It always looks flat. It looks like this. Okay? So, you see this yellow layer over there? It's present there, but it's absent over here. Is that right? So let's say that's the Grand Canyon series, and there's a layer missing there, but it's present in another part of the world. So how do I account for it being missing? Easy. I say the layer was there, but it was a period of erosion before the next layer, the red one above it, was deposited, and so it was rubbed out in this area, and then the next layer was put on top. That's why it's missing. Is that what science says? Yes or no? You saw it on the board, right? Here's another solution. The layers actually are never what science says. In fact, they form during rapid deposition during the flood. And I have 3 buckets in the front here. I have a huge bucket of black mud. And I have a small bucket of yellow mud. And I have a big bucket of red mud. Those 3. Now I take the black mud, the big bucket, and I go, phew, and I spread it across this hall. And everywhere there's a layer of mud. Then I take the small bucket and I go, phew, and it only spreads as far as in the front here. Then I take the big bucket and I spread it again. If I make a section at the back, how many layers have I got? 2. If I make a section in the front, how many layers have I got? 3. So I must conclude that millions of years of erosion in the back removed the layer that's missing. I could have another model and I could say, hang on a second, maybe there wasn't enough mud to get there. Are you with me? Everybody with me? Okay. Let's see if we can do something about this. Well, some scientific publications, just to show you that other scientists agree with us. He says over here, 20 million years of erosion in Australia. Some areas even more remarkable, 200 million years of erosion, epigene attack. And that these rocks are even still there. The survival of these paleoforms is in some degree an embarrassment to all the commonly accepted models of landscape development. Why are they still there? This one over here says 2 rock layers, one Paleocene, the other Eocene. I could see them perfectly. There's the one, there's the other one. Outcrops, excellent. But I couldn't find, even at close inspection, that 15 million year old gap. No sign of there ever having been a surface. Here's another scientific publication. It says, well, the limestone seas that spread in the past over the earth were incredibly flat areas of the world. So the world was different according to these. Here's another one which says, and if this was ever the surface of the earth, like they say, why is there no deep leaching? Why is there no scour, channeling, residual gravels? Why doesn't it appear as if it was the surface of the earth? Okay, let's put another model together. It's pouring cats and dogs. It's the flood. And the fountains of the deep are breaking loose, and the water cascades and mud flows start flowing over the earth as the water rises. And the mud flows with each earthquake. Do you know what happens in South America if there is a major rainstorm and there's a mud flow? What happens to some of the towns and cities? Whew, gone. And do the people have time to get away? No, they're buried instantly. Okay. So let's assume all this is happening, and slowly the continent is even being depressed, and huge earthquakes and mudslides and rain and chaos like you have never seen it before. We're going to simulate it here. This is called the turbidity current. It's an underwater or shallow water mud flow. In 1929, there was one of those off the coast of North America, and a piece of the continental shelf broke loose, and it soared under the ocean, a wall of mud flowing under the ocean at a speed that after 3 hours, 3 minutes, let's make it 3 hours, it was 300 miles out to sea. Now, if you were a creepy crawly or a fishy wishy, and here comes a wall of mud at you at 100 miles an hour, what would happen to you? You would swim and you go, what would you be? You would be an instant fossil. You would be covered in mud instantly. But I'm not going to talk about fossils. I'm going to talk about that next time. All right. So here we've simulated a little bowl. And here is an upland area. Here are some hills and mountain ranges. And we're going to have a little earthquake. And some of the shelf will break loose. And it will flow over hills, over valleys, right across everything in the form of soft mud. There it goes. Can you see that it's flowing down the valley, up the valley? Can everybody see that quite clearly out there? Okay. And then it'll settle out. Now I want you to look at the next layer, which will flow over the soft mud. By the way, it fills in the valley, and it flows over the top, and it's a nice soft mud layer. Flows over the valley, over the top. And as it fills it in, we can see that the bottom has, the valley has a much thicker layer. And that's what the geological column looks like. At the bottom, it's filling in valleys, and at the top, it's straight. Now we have a second flow over the previous one. So we have a mud flow going over the mud flow. Notice how it swirls in the front there. Can you see that? Do you think it's possible that you could whip some of the bottom into the top? I mean, the bottom is soft mud, and you're rolling mud over mud. Is it possible as it swirls that some of the dark brown could go, or the reddish mud can go into that brown layer? Yes or no? Yes. Okay, I like that. Here's another layer. Notice the swirling. And this is all happening in water, and it settles out, and all of them are soft. Surprisingly little mixing. Next layer over the top of that. There we go. See how nicely it flows now? Everything's flattening out. And let's have another one over the top of that. This evolutionary process takes a while, so be patient. There we go, there's another one. And there goes another one. Okay. Last one. Guaranteed. And now we're going to have a nice close look. What do you see? Well, you see layers and layers and layers, and they have got flat contacts, right? The contact is flat. That's exactly what it looks like in the Grand Canyon, yes or no? Yes. Okay. And we continue and have a look at something else that's interesting. I hope that we can see it as we move in over here. And we move a little bit closer. I'll stop it over there. Can you see that at the bottom over here it's lumpy? There are some lumpy pieces over there. All right, that's because when you're putting rocks and stones and mud into water, what settles out first? The stones, the heavier stuff, and the mud higher up. So you have these graded coarse to fine. Now, if they are graded coarse to fine, then they never ever formed over millions and millions of years. But they formed rapidly by some process such as this. It's the only explanation. And if you look at the contact lines, you see very little mixing. You would expect a lot more, wouldn't you? Incredibly, even with those bumps and swirls, very little mixing. But occasionally, you do see some mixing. And if you look closely, you would be able to see some mixing over there, for example. Can you see it? There are some places where you could actually find mixing. Okay, let's go into the world. Let's go to Switzerland. These have all been identified as turbidites. Those in Texas, they've been uplifted. They were first flat. All those layers are turbidites. How do we know? They're graded coarse to fine. All of those in Texas, these thick ones, there's huge ones, thinner ones, small tremor, thin layer, huge tremor, big layer, goes far, goes not so far. All turbidites. These turbidites over here in New Zealand, graded coarse to fine, ripple marks over there. This one over here, coarse to fine, all the way up. Next turbidite, coarse to fine. The whole geological column, everywhere in the world, no matter which continent you go to, has these turbidites and graded coarse to fine. What does that tell you? This tells you catastrophism. Major catastrophe, and water was the consequence. Science say, whoa, 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 you're not telling me that the geological column formed rapidly and come with a short chronology. We have deserts in the geological column. Like here at Zion Park, you have a dune, which they say is desert. Wrong. This is not a desert dune, this is an underwater dune. The angle of deposition, the way, the size, everything about it talks of underwater dunes like you have at the mouth of the Amazon River. Latest studies find that. So, you could have had continents in the beginning, no mountains like you have today. You have these continents up there, the pre-flood continents. The mountain ranges of today don't exist. So don't say, how could the flood have covered the high mountains like Everest? They didn't exist. They weren't there. Then you depress the continent in the next one down, and you lift the ocean floor and you pour the sediment over the land. That could answer why there is so much marine sediment on the land where it shouldn't be, and so little in the ocean bottom where it should be. Isn't that confusing? I would find that very confusing. And then you lift it up again, the continent, and this mud is in layers, and it slips and slides as you form these new mountain ranges, as you push them up through the process of orogeny. And of course, they slip and slide and fold. All right, let's have a look at some of the interesting contacts. We said if they were both soft, it should be possible to mix two layers here and there. Did we say that? Okay, so you could have some mixing, or if the bottom one was soft, you could depress and change the shape of the bottom one. This slide over here, I've shown it at many universities, in many geological forums. It really is a nightmare slide. Because what you have here is two layers, one supposedly millions of years older than the other, and yet this is a turbidite flame. Can you see it? And this is not a bump standing out there that has been covered by the other one. No, this is a total mixture, getting less and less and less as you go up. So this layer at the top rolled as a soft mud over the previous one, whipped some of the bottom into it, mixed it, and carried on. So how old are those rocks in terms of their time spaced apart? We're talking catastrophe. We're not talking millions of years at all. Here is what we call a load cast, depression of the one into the other. So this layer over here is pushed into the other, and you have compression zones in the bottom one, like somebody putting his foot into mud and going squish, you know, squish. Not solid rock. Here is a mountain in the Alps that is folded in an S. There's another one. Look at that slipping and sliding. Now, how do scientists get these layers that are layers of rock that obviously formed like this, flat, folded like that? How do they do that? Well, if they're millions of years old, then they're solid rock, right or wrong. If they're solid rock and I'm going to go, what happens then? What happens to them? They must smash apart into thousands and thousands of rock chunks, am I right? But they don't. They fold. So science has to put them into the bowels of the earth, heat them in the magma, push them up, fold them while they are hot, and then there they are. But many of them have no sign of heat. Many of them are cold sediment deposits. Many of them have fossils in them, no sign of heat. This is very confusing. But if the layers were all soft, no problem. Take a look at that. This comes from Africa. You will notice the African ones are more exciting than any of the others. Can you see that? Isn't that beautiful? Around it goes. Next one over here. Look at that one. Down and up it goes. Beautiful folds in these mountains. All right. So science says each one was millions of years older than the previous one, was solid rock. Now let's have a look at this over here. Very interesting feature. Here stands a finger. Ding! There it is. And it's standing there, and the soft brownish rock over here, muddy sort of sandy stone, has been eroded away. But this fellow is slightly harder than it, so it's standing there. Where'd it come from? Well, if you have a study of that, you'll see that it actually comes from the layers beneath. So in these rock layers here in Kodachrome Basin, you have these pillars going, and they're pushing through the layers of rock. Now, hang on a second. If each one of those is a solid sheet of rock, how do I squeeze the bottom one through the others? Is it possible? Only if I liquidize them, right? If I make them a liquid. If I have 3 layers of mud and I put some toothpaste tube underneath it and I go squeeze, could I shoot the column through them? Yes or no? Exactly. If I put pressure on a liquid, it actually forms columns like this. So I would like to suggest that all those layers were absolutely soft, and that pressure from earth movement and earthquakes or whatever pushed up columns like this, and there they solidified together, leaving these stark reminders of a once uniform liquid consistency. Okay, evidence number 1. The straight line shows that they must have formed rapidly. They were never the surface of the earth. Where's the erosion? No sign of it. Flat. Second evidence, if they formed rapidly, they must have been soft. Is that right? We showed you evidence for soft. The third thing I would like to point out is that if there was a flood, there must be a lot of evidence of a lot of washout. Is that right? Okay. The Grand Canyon, for example, goes here. This is the map of the geology. There's the basin, the valley, and there's the uplifted area. It's a hill. and there's the Grand Canyon. Now, what formed it? The river. Now, do you know of any rivers today that travel and then go over the valleys to cut a crack in the middle? Do you know about anything like that? It's a major, major problem. The river is younger than the hill, and there are differences and problems in getting the river to go over the hill. Impossible. Whereas with this model, the waters are covering the earth. Then you have an upwarp over here. You lift up this portion quite rapidly, and as you lift it up quite quickly, is it possible it could crack at the top? If you lift it up at the bottom, like this? Sure. And it cracks and the water runs through, and you have an instant canyon. This is a relic of the flood and of a major water catastrophe. Nothing else. No matter where you go in the world, whether you go to the Grand Canyon, whether you go to Zion Canyon, now here you have a narrow little canyon, all the way up to the top. In some areas you can touch the two sides. Incredible stuff. How did that form? There's some more of it. If you go to Africa and you go to Namibia, some beautiful erosional features as you see them over here. Wonderful stuff. And the layers, just like everywhere else in the world, watermarks, ripple marks. And the Fish River Canyon, not as spectacular as the Grand Canyon, but very peaceful. Not so many people, and nice to walk in, and very beautiful. And please notice something. You can see the layers, just like in the Grand Canyon. And the river itself, the canyon, is cut in a V shape. Can you see that? It's V-shaped. Now that's very important, and don't forget it. Right around this meander, it's V-shaped. This is the famous Ochrabis Falls. This is the Orange River Canyon. There it is. And if you look at that, you will also see it's much like Zion. Sort of more sheer, but occasionally forming a V. And in the water, occasionally you see these rock washouts. And here's one, high up on the mountain, what we call a whirlpool washout. Let me show you another one. There's another one. Isn't that beautiful? How did that form? Well, you see, who's ever sat next to a river and watched a whirlpool form? And it goes, and it's gone, right? Now, imagine the earth comes up, the water rushes down, there's a whirlpool, and it goes, and the water's gone. Could it have sucked some of the mud out? Yes or no? Absolutely. But what if that was solid rock? Would the whirlpool stay in one place and go until it drilled the hole? Yes or no? Highly unlikely. Okay, some scientists say, the stone went round and round and round. But this is high up in the mountains. These are, I don't know what that is, never mind. Here's one high up in the Cedarburg. This rock was soft when this formed. Do you recognize this? That's the goosenecks. And please note again, you have the V shape. Can you see that? And science would have us believe that this Colorado River took millions of years to wash out the goosenecks. But a scientist came along and he studied this in great detail, published it in a very reputable journal, Science, and he said, if it's V-shaped, it must be rapid. Because a slower time period would undercut, and you would have something like this. That must be rapid, and that little piece down there must be undercutting, must be more slow. So that is post-catastrophe, that is catastrophe. Here is Kanab Creek, the meander, washed out in a few seconds. Bryce Canyon, beautiful. If you haven't been there, you really must go. What washed out all this tremendous canyon? Was it millions of years of slow erosion, or was it a rapid washout over time? And look at the valleys and these beautiful rock formations that you see over there. I was there just when it snowed. Here is another valley that's very interesting. This is Monument Valley. Can you see these monuments? Relics of layers that once were intact, contacted with one another. In between, everything is gone, but these stubborn little mounts are standing over there. Or those were the two most stubborn mountain sort of peaks that you can imagine. Everything in between has been washed away by millions of years of erosion, but those two guys refuse to move. Or is there another solution? Or those two, don't they look great? Navajo twins. Well, I was traveling here in Africa, and what you see here is a Basutu hut, and this is a donga. This is a rapid washout that happens after a rainstorm. And here you have it. And look what you see. There you have a valley, all washed out. There you have a peak and 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 a peak. Now, millions of years of erosion washed everything in between away, and these guys remained. But we know it was not like that. This was rapid. So increase the scale, make the scale larger. Here's another donga. Sitting up there is not a rock hyrax. I think it is my wife. And here you have V-shaped in this donga. So this again is rapid washout. Again up there in the mountain, these massive slits high up in the mountain. Rapid washout is the only explanation, or this is absolutely phenomenal. If you look over here, you can see the mountain is undercut. Can you see that? So now how did that happen? Well, let's say these layers formed, and then the waters rushed down as this continent was raised up, and this is mountain, so you have rushing water, and the water gets flat very quickly, shallow, and rushes down, and starts with its force undercutting the mountain. But before everything is gone, the water is gone, and so we have the tunnels underneath. This, by the way, is next to a road, where a highway's water comes off, and the water flow in this area is so quick that it just cuts straight down. A little Zion Canyon. That is as deep as this roof, and it stays like that all the way down from this rapidly shallow flowing water. Look at this guy sitting over there. Why is he there? I would like to suggest that it's not millions of years of erosion, because he's absolutely smooth underneath there. You can see the erosion on the top there. So what happened was, this mountain range came up, like that. The water rushed down the valley, and before this rock was gone, what happened? The water was gone. And so it stood there, solidified, and you have these relics. So if you go into a valley, and you see these mounts, sediments remaining over, you see these strange structures, it's not such a problem anymore. If you take this one over here, this is Australia, Ayers Rock. Millions of years of erosion either left it there and refused to take this thing away, or the floodwaters took everything in between away. Now science will have you believe that that is not possible, because it surely takes millions of years for rock to form. Is that right? Alright, how long does it take for rock to form? It depends on the conditions. That's the point. Depends on the conditions. Have a look at this slide. This is from the HMS Her Majesty's Service, Birkenhead, which sank off Danger Point in the Cape in 1852. And what you have over here is a piece of ceramic pottery over there, and a bottle encased in solid rock. So you have two choices. Either that bottle and that ceramic pot are millions of years old, or this rock didn't take so long to form. Here's another one. Here is a bell, a ship's bell, encased in solid rock. You have the same two choices. Either that's a millions of years old bell, or the rock formed rapidly. How long does it take for stalactites and stalagmites to form? They will tell you millions of years. Well, here's one that formed when they pumped water to this district, and it grew in front of their eyes. They got so excited they made a monument of it. You see, it doesn't have to take millions of years. Crystals, gemstones, millions and millions of years of processes. Well, I was stunned. I was invited to this gemstone dealer, this very prominent gemstone dealer, and this individual was in tears. They had bought from a mine in the Congo malachite, very expensive gemstone, and exported it to the United States for thousands and thousands of US dollars. It's good to export to the United States because you get lots of money because the dollar is so strong. And these malachite stones form in malachite caves, only under certain conditions. Now you can see those pillars. This is an absolute superb example. It's probably worth about, whatever, 30,000, 40,000 US dollars, this particular one over here. And then they exported these to the United States. And one of them broke in transit, and it was sent back. And what a shock awaited the gemstone dealer. Here you can see something sticking out. Can you see it? Do you know what that is? That's a wire. And it's a copper wire. And if you look over there, there's another one. It's a copper wire. Let's enlarge that. It's absolute perfect malachite. No doubt, it's gemstone quality malachite. Millions of years for a rock like that to form. Here you have the wire. In their stress, they broke the next one, and guess what they found in the next one? Wire. And so now they know that the miners have figured out that under those circumstances in those caves, if they put wires there, and they let the water run through the rocks, which have the capacity to have all the elements for malachite, then the malachite forms rapidly. And within a few months, they can deliver the next batch, and the next batch, and the next batch. So how many millions of years is it old? That is the question. How old is this island of Surtsey over here? Well, it's just a couple of months old, and yet you can see the beaches are perfectly ground down. The island formed in 1967. 8 months after it formed, that is what was visible. I would like to suggest that there are two possible models. Of course, there are millions of questions in your minds, but just concentrate on the rocks. Is it possible that the rocks formed rapidly, and that is why they are flat, that they formed catastrophically in water, and that they were all soft, and that the fossils in them are a record of something totally different, but you'll have to wait for the next exciting episode, which comes straight after this one.